Du lundi matin, séminaire étudiant RQMP. Donc aujourd'hui, on va avoir une seule présentation de Martin Schnee, qui est étudiant à la maîtrise à l'université de Sherbrooke, qui a commencé ses études à l'université de Nantes en France, et puis qui nous est venu à Sherbrooke et maintenant fait sa maîtrise donc, dans le groupe supervisé par Stéphanos Courtis. Il va nous parler aujourd'hui donc de thermalisation quantique, je crois en anglais, si ça ne me trompe pas.
Oui, exactement.
Ok. Et juste une petite question, est-ce que tu préfères prendre les questions pendant la présentation ou après la présentation?
Pendant la présentation, c'est OK.
Voilà, donc n'hésitez pas à vous démuter quand vous voulez poser une question et à poser directement la question à Martin. Donc la présentation, c'est à peu près 40 minutes. Voilà, bonne présentation.
Exactement. So thanks a lot, Nicolas. So I'm very happy to have you here. So for the presentation of the project I do with Stéphanos Courtis at Institut Quantique. And so this morning, I would like to talk about rather simple things, finally, that you all know about. So first, the dynamics of isolated quantum systems, the simple thing that you've all learned in your first quantum mechanics course. Second, the process of thermalization, so this process by which systems made of a huge number of particles like gases, solids, and so on, reach a state of global equilibrium. And finally, entanglement, so this really quantum mechanical feature, which is at the root of these modern and rapidly evolving fields that are quantum computation and quantum information. So when put together, these three things give rise to a very interesting and challenging puzzle, I would say. And a puzzle to understand really the foundations of statistical mechanics. So, and in this puzzle, entanglement may play a key role. So I will talk about that, and then I will explain how I'm interested in these deep questions in the context of a special kind of many-body phenomenon called quantum many-body scars. So follow me. So first, let's remind ourselves how a quantum system evolves, just to make sure we are on the same page. So what I'm interested in my project is to study the dynamics of quantum many-body systems, meaning the evolution in time of systems made of a huge number of degrees of freedom, and usually interacting with each other. More precisely, I focus on isolated systems subjected to their own dynamics, meaning the dynamics which is generated by their Hamiltonian, which is so dynamics, which is unitary. So in these systems, they are closed, so their quantum state stays pure. As I said, their evolution is thus unitary, meaning it's reversible. And usually, for a simple Hamiltonian, I mean, not time dependent, the evolution is just a rotation in the Hilbert space, really simple rotation. So this evolution operator brings an initial state, here psi 0, to an evolved state at a later time. So the thing is, if we start from an eigenstate of H, the unitary evolution doesn't give something really interesting physically. It just adds a global phase in front of the initial state. So nothing really, nothing physically relevant here. It's thus more interesting to explore the out of equilibrium behavior of the system, meaning what happens when you start from a state which is not an eigenstate of the Hamiltonian. So, for example, you start from a state which is like very ordered. So the spin states are really well defined. This is not a superimposed states. And so this is usually not an eigenstate in system with lots of strong interactions between the components. And unitary evolution will give you an unknown state that you want to find. And this is really much more interesting because the final state will be really different. Okay, but why is it interesting? This is interesting because we wish to have a quantum picture of the thermalization process. So maybe let's recall what is thermalization, at least classically at the beginning. So thermalization is just the process which make a complex system tend to a state of equilibrium such that it can be easily described by a small set of macroscopic variables. This is crazy because the kind of system we're interested in have like billions and billions of variables, of microscopic variables, but in this situation where the system thermalizes, you can describe it with only like four variables: pressure, temperature, volume, and so on, and more specific variables. But this is pretty amazing already. This thermalization process is based on the idea that all phase space is explored in a reasonable time. So as you know, in classical StatMech, the state of the system is described as a point in the phase space. And if you want to be able to describe the state of the system in equilibrium statistically with StatMech, you have to assume that all phase space can be reached from any starting point. And this is possible because such complex systems have a dynamic which is very sensitive to initial conditions, meaning they have a chaotic dynamic. In general, it's because they have a really small set of conserved quantities compared to the total number of degrees of freedom. And this chaotic dynamic, so it just means that if the system begins in a slightly different state at the beginning, he will encounter a completely different trajectory, and the difference between the two initial states that was really tiny at the beginning becomes exponentially large. And that's what allows us, in the end, thanks to ergodic theorems, as it is called, to treat the system statistically. So, as I said, ergodic hypothesis, and this assumes a chaotic dynamic, which is defined as a high sensitivity to initial conditions. What we would like is a quantum picture of this process, a quantum picture of thermalization. So, as we've seen just before, quantum dynamics, is rather simple for even for complex systems if they are closed, and thus it should give us back thermodynamics at some point. So thermodynamics for closed systems, of course. The thing is, chaos, which is at the root of thermalization, classically, and quantum mechanics seem incompatible. Why? Simply because in quantum mechanics, so the state of our system is described in not in the phase space, but in the Hilbert space. And in Hilbert space, if you take two vectors that are at the beginning very close to each other, and you make them evolve, there is absolutely no way for them to evolve apart at an exponential rate. So the distance between them stays the same. And this is due to the linearity and the unitarity of the evolution in quantum mechanics, which is a really fundamental axiom of quantum mechanics. So there is really a deep paradox here. Moreover, some quantum systems have been discovered more or less recently to resist the thermalization. So they are many-body systems, quantum many-body systems, but they do not thermalize. So for example, there is this many-body, so-called many-body localized phase, where with a complex interplay of interferences, particles stay localized on the sites. And yeah, so this is there is really a problem here, which has to do with the foundations of quantum mechanics. So here we have like two options. If the linearity or the unitarity is the problem in quantum mechanics, then maybe statistical mechanics only makes sense quantumly in the context of open systems. So this is an option, but this is not the one we choose to explore. Another option is to find another definition of chaos that fits quantum mechanics, and thus allows us to get statistical mechanics back in some way. So many different paths are investigated to redefine quantum chaos, in fact. And one question we can ask is, of course, how to redefine quantum chaos, but what question we can ask is how to find how to find quantum signatures of chaos, and what kind of signature could we find in many-body systems. So, even though we are not sure yet which, so just as a reminder first, I like to talk about entanglement because to solve this problem, entanglement may play a key role. So just for us to be on the same page, I will just recall in a hand wavy review what is entanglement. So entanglement is really this special kind of quantum correlation where you can have all information about a system. So here, for example, a system of two particles, which can be, each of them can be in two states. And you can have, they can be in a state where you have the maximal information about the whole system. So meaning you have a pure state for the whole system, which by definition gives you the maximum information. But you have no information about the subparts. So meaning, if you want to have only, if you want to ask the question, what is the state of the particle A, for example, only, you cannot write a pure state. You cannot write a state which gives you the maximal information. The only thing you can write is a state that is what we call mixed. So it's a classical distribution of quantum states, meaning you have no information. And in the case where the state is maximally entangled, like here, you really have an equally distributed, an equally distributed set of possible pure states. So you have no information about what pure state would fit to the subsystems. So, for example, but you have all information about the whole. And for example, here, what you know is that both particles are in the same direction, have the same spin. In this one, you know that their direction is they have opposite direction, but you don't know the state of the subparts. So now remember, here we are looking at isolated systems under unitary evolution. It means that the final state has to be a pure state. If we begin with a pure state, it has to be a pure state at the end. In this picture, this final pure state has to realize thermalization. So what does thermalization lead to? We just saw that it must lead to a state for our quantum many-body systems in which we have all information about the whole system, meaning we know the macroscopic variable that describe the system, but we have no information about the local degrees of freedom. When I mean no information, it means that we don't know their pure states. We can have a classical probability distribution for them, but we have no maximal information about the local degrees of freedom. And when you think about what I just said about entanglement, this is pretty much the definition of a highly entangled state. And this fact, in fact, motivates the idea that entanglement may play indeed a key role in understanding the process of thermalization from a quantum point of view. So in particular, in particular, our goal really is to measure this inaccessibility to local degrees of freedom, what I call here the scrambling of information, meaning the state, the pure state, the information about the pure state of each particle has kind of diffused into the whole system. And we want to measure the degree of scrambling of a many-body system with the hope that it will allow us to, in some sense, characterize the chaos and thus thermalization from a quantum point of view. So let's make a pause let's make a break with the concept, and let's talk about the model I'm studying. So the model I'm studying is called the PXP model, so not really a fancy name. And it's a really simple model. So this is simply a 1D chain. A 1D chain where each state can be in two states. So a basis state and so a ground state and an excited state. And thus you can consider them as like spin 1/2, kind of. And on these sites, you have strong local constraints, so in the form of strong interactions that take the following form. So each spin interacts with its closest neighbors. And what is special about this interaction is that the spin in the middle, so if I zoom on it, the spin in the middle can flip only if its two neighbors are in the ground state. So how do you express that? The flip, on a two-dimensional system, you express that with the X polymatrix, so which flips between ground and excited states. And on the side, you have terms that are in fact projectors, simple projectors on the ground state. And so to build the whole system, you just make a sum of the roll sites of three body terms like that. So as you can see, a really simple model, but with rather unusual interactions. So let's have a look at this at the effect of this projection, because this will be the key thing. So so what this projector does is really constrain the dynamics. So for example, it allows only, if I take a state of only 3 sites, it allows only for a dynamic between this kind of configurations. When you have two sites in the ground state and something in the middle. It forbids, it's even discard lots of configurations. For example, these ones are completely forbidden because here the two extremal sites are not in the ground states in each case. And in fact, in a many-body state, it discards all configurations where we have two neighboring sites in the excited state. So maybe you can see it just because if you have, so imagine I have two neighboring sites in the excited states. I can have whatever I want here or whatever I want here. This projector will project the state to 0. So it has a really weird effect on the dynamic for some states. So remember that the dynamics is given by this simple evolution operator generated by the Hamiltonian. Our Hamiltonian is just a sum of all these projective terms. And it means that for some states that have really a crystalline order, so for example, a state which with alternating white, black, etc. For this kind of state, the ensuing dynamics will be really special. So here I have a graph to show that. So this graph this graph shows you only the states that are allowed by this constraint that will be allowed during the dynamics. So to build this graph, you have to use a kind of trick that that the people used in this article. So this graph is from their article. And what is interesting is that you start from here. So you start from this, as I was saying, very ordered state. And then you apply the Hamiltonian. So each term, you apply the Hamiltonian, each term in the Hamiltonian. And here, you keep only the states that are not discarded. So there are only 3. And the difference between this layer and this layer is only 1 flip. And then you apply again the Hamiltonian, and again, and again, and again. And what you see is that you kind of come back, instead of having like a really growing, a superposition of growing size, what you have is that you come back to a very ordered state, which is in fact the complementary of the one we had at the beginning. And if you had to continue, you would have the same graph, but in the inverse direction. So you would get back this state. So this kind of really weird dynamics for these special initial states is called quantum scars, quantum many-body scars. This is due to, so you can represent these all the eigenstates of the.
Martin?
What?
Martin, we have a question. André Bernien was asking if you consider periodic boundary conditions.
Yeah, of course. This is periodic boundary conditions and translationally invariant. You can also consider so open boundary conditions. It also works, but of course on the boundaries you will have so boundary effects. So you'll see less these effects. Yes. Is it okay?
Yes, I think it's okay.
Okay. So so you have these special states, these special scar states, which have this kind of revival, really strange revival, and these kind of long-lived oscillations, because you understand that during the dynamics you will kind of come back and back again to these states. So some people have made it in cold atom experiments, and this is pretty amazing. They did it in 2017 at Harvard in the Looking group, and so they used a 1D array of cold atom that were and so with a engineered special engineered magnetic field, so magnetic, electric for the traps and magnetic field. You can engineer such a chain with these very strong interactions between the atoms. The atoms are put in a very excited state, can be put in a very excited state called a Rydberg state, where the outside electron is very far from the rest of the electron cloud. And you can engineer this kind of very constrained interaction. And so what they observe is really this phenomenon. So here you see for a small number of spin of atoms, sorry. So here you have like 9 atoms here. You have the sites here. And so this first step is to prepare the atoms in the initial state, which is this kind of alternating state between ground and excited. And then they make it evolve freely. And what they see is really this kind of revival. So there is a kind of mixing and then a revival of this periodic order, sorry. So this observation really started the interest for understanding this weird phenomenon, and maybe the weirdest thing with that is that it makes the whole system thermalize really slowly. We don't even know if it thermalized completely. And thus, this was really a good model to explore the process of thermalization and So from a quantum point of view, and apply the tools we want to apply. So the tools I will show to you right now. So how to probe the scrambling of information in many-body systems. So first, how to quantify the amount of entanglement. Remember that we said before that when our system is in an entangled state, then we have a maximal information about the whole, but a very poor information about the parts, even no information if we are maximally entangled. So what does it mean? It means that the more entanglement you have for your whole system, the more the subparts will look kind of a classical distribution, classical and random. Thus, a way to quantify entanglement would be to quantify the degree of kind of classical randomness on average. So how you do that? You do that, you take your system and you cut it in half in your mind, in two subparts, A and B. And by a special procedure called the partial trace, you can build the state. So this what we call mixed state, which is you can see it as a classical probability distribution of quantum states of these subparts. These mixed states take the form of a matrix, and if you diagonalize this matrix, you get this classical probability distribution. And then what you can do is use a measure of the randomness of a probability distribution called the entropy on this probability distribution. So this is called entanglement entropy because of course it will measure as it measures the degree of randomness, it measures the degree of entanglement between the subparts. And what we are interested in for us is the growth in time of this entanglement entropy. So here I put the formula. So the trace really means that we are summing over the diagonal terms of the matrix. And you can really see it as a kind of average. And this is the problem, because this is a good measure of entanglement, but this is not really precise, because it doesn't give so much information. So we want more, and what we want to explore and we want to characterize is really the structure of this probability distribution that we call entanglement spectrum. So really characterize the structure of the spectrum of the density matrix. So how to do that? So this is called entanglement spectroscopy. And this is based on tools from random matrix theory. And basically what random matrix theory allows you to do is that it allows you to kind of make a statistical analysis of the structure of a matrix. So, for example, what people realized, so it began in the 1950s, and what people realized is that you take a matrix, you build it term by term by picking random numbers from a really simple distribution, for example, a Gaussian distribution. And then if you look at the spectrum of this matrix, so you diagonalize it and you look at the spectrum. And in particular, for example, you take your matrix and diagonal matrix, and you look especially at the spacings between the eigenvalues and at the relative spacing between the ratio between consecutive spacings. So what it will give you, you make a distribution from this information, and what it will give you is a curve representing this distribution, which is universal for this whole class of matrix built from the probability distribution that you've picked at the beginning. So you can really characterize the degree, you can characterize the kind of the structure of matrices from universal quantities like this. And here, so this is the kind of curve that you obtain. And for example, if you build your matrix from a uniform distribution, you will obtain what we call a Poisson distribution in red of these level spacings. If you begin with a completely random distribution, you will have this green curve, which is called Wigner-Dyson distribution. And you can have everything in between completely random and completely uniform. And this is the kind of tool we want to use on our density matrix. So recent evidences and mainly numerical studies have shown that there is really a strong connection between this entanglement spectrum statistics. So this probability distribution built from the density matrix spectrum, and the fact that the system is chaotic. So there is a strong connection, and more than that, people in the 50s they used this kind of tool on the Hamiltonian matrix. And they thought that it was a good way to characterize thermalization, thermalizing systems or chaotic systems. For example, they used it to study the heavy nucleus and so on. And but with this new kind of system that resists thermalization, it has been shown that this old way of measuring chaos with the Hamiltonian is not doesn't work every time. And there are some systems for which you find the Wigner-Dyson distribution, but they do not thermalize, for example. And lots of numerical evidences have shown that doing this kind of analysis on the density matrix allows you to distinguish between this for these systems where the previous method wasn't able to do so. So more than that, since we want to study how our system scrambles in time, we want to have a kind of a distance measure between the actual distribution of our system at some time t and what would be a completely random distribution. So, for example, a distance measure between the distribution of our system in blue, for example, and the distribution that here is in green, which corresponds to a completely randomized system. And for that, we use a tool called relative entropy, which serves really as a distance measure. So this tool is so it's really like doing statistical mechanics on the structure of the density matrix. And I have to say that this tool is only relevant really at long time scales, because we want the density matrix really to have some times to equilibrate. if the scrambling happens very too quickly, then it doesn't make really much sense to use this. So, having said that, maybe it's time for a quick summary, and then we can see the simulation and the results. So, so what we want is really characterize the entanglement complexity via the degree of information scrambling in the model. And the question we ask is, can we make statements about long-time dynamics of the PXP model? So with these oscillating behaviors, meaning does it thermalize completely at some point or not, and in which way? So simulation and results. So remember this graph. The nice thing to do our simulations. Oh, something. Okay. The nice thing to notice if we want to make efficient simulations is that this graph represents all the allowed states, and this is for a 6-qubit, six site lattice. So for 6 sites, the entire Hilbert space is contains 64 states. But here, the allowed subspace is only contains only 18 states. So it's really much smaller. As what you realize is that with the size of the systems, the size of this effective subspace scales with the power of the golden ratio. So it's still exponential, but really, as you can see here, it's much smaller. The selective Hilbert space is much smaller than the total Hilbert space, and we can use that in a clever way to make our simulation much easier. So it really allows for efficient exact simulations, and thus we can build a code that generates directly the evolution operator in the physical subspace, so really a much smaller matrix, and the associated graph for any number of states. And thus, really, you can, on a laptop like the one I have, I can simulate 16 qubits and obtain so the relevant results in 3 minutes. So it's really efficient. I would say the only problem, the limit is really that to compute the relevant statistical quantities, I have to re-embed the state I obtain, the final state, in the large Hilbert space. So this is really the limit. I still have to create a huge matrix at some point, but not as huge as if I had to simulate it completely in the full Hilbert space. So first thing I want to show, of course, these are preliminary results. Is the entanglement entropy, this average measure of entanglement. And we start from this crystalline, really ordered state for which we have this weird dynamics. And so for a standard system that would really thermalize completely standard system, what we would see is an entanglement entropy that in time grows really fast and then saturates at this gray line, which is the theoretical maximum of entropy a system can have. For these really constrained 1D systems, first, the theoretical maximum is a bit lower due to the constraints. And for this special scarce states, as you can see, the rate of thermalization is much slower first, and you have these weird oscillations. So meaning really that the systems begin to thermalize, and then the entropy decreases, which is really weird in thermodynamics. decreasing and oscillate in such a way. And so as you can see, so here the time unit is really, I mean, I put everything to 1. So I really have a standard time unit. But as you can see here, the system doesn't appear to thermalize, or maybe really slowly. But here I will have to push this for very long time. So here it's for 16 qubits. What I can do then, so still for 16 qubits, is that I can compute this distance measure, the relative entropy, between between the level spacing distribution of my density matrix at time t, and what would be a completely random distribution. And so I have this really awful curve that seems to decrease with time. So, which is normal. At the beginning, we are in a very ordered state, so very far from a random distribution. And then we are approaching thermalization, but we do not reach 0. So the reason why this is awful, it's because in fact, with 16 qubits, even though with 16 qubits, the number of, so the size of the Hilbert space and thus the density matrix would be already huge. In fact, due to the constraints, the number of eigenvalues of the density matrix that are non-zero and that we can use to draw this kind of statistics is really small. Is really small. And here I plotted in green. Focus on the green curve. I plotted the number of eigenvalues of the density matrix, so which I call singular values for a technical reason. But I plotted this number, and so the ideal maximum of non-zero values would be 64 here. But as you can see, I saturate at 15, and I mean to do a statistics with 15 values, you understand that it's not really significant. So sorry. So what we have tried to do is remember that these data come at the beginning from the fact that I cut the system in half, and we have tried to come up with a kind of cut which alternates between the sites, which is really artificial. It doesn't have really a physical meaning, but it kind of artificially increased the number of values that I can use, the amount of data. But so it was our hope. But as you can see, it's the yellow curve. First, it really oscillates, and it doesn't go really higher than 20 values on average. So not really good, not good at all to do a statistics. So really here, we think so for the future, we need to increase the number of sites in the simulation. This is really critical, and from our estimation, something like 25 or 30 sites will be enough to get all the data we want, meaning at least a few hundreds of values to have good statistics. So this is really the next step. But for that, we need to run the code on a server, because my laptop won't have enough power for that. So yeah, so this is the future. In the future, we want also to access more refined measurements, refined measure of the degree of scrambling, so we can measure higher moments of these distributions. So my conclusion will be really simple, because the message here was really, so the first thing that I wanted to show is really that you can, this project is really the meeting between quantum matter and quantum information. and the fact that you can study one with the tools of the other, it really gives you a different picture of the physical processes. And more precisely, there is really an interest in the study of the dynamics of structures and patterns of entanglement and the complexity of these patterns in quantum matter. There are other kinds of systems, for example, quantum spin liquids, where you really are a topological matter, where really you can infer the properties of the material from the entanglement pattern. So what I would say also beyond the application, in that systems with such an unusual dynamics seem really promising for future applications, in particular in the field of quantum information, because such systems that do not thermalize and which have this revival, really, it means that they, in some way, they remain coherent. So the information is not lost. So there is an interest for that, but we have to understand their structure much more. So I'm finished. Thanks a lot for listening to me. And if you have questions, please ask.
Thank you very much, Martin. So if you have a question, please ask them directly. So if nobody has a question, I have one. When you showed your previous slide, your results that seem to show some periodicity, does it have to do?
Here.
Yeah, here and then later. Does it have to do with the fact that your Hamiltonian seems in your subspace seems to have also this periodicity of going from the left to the right and then to the left, what you showed on the presentation of the PXP Hamiltonian? Does it have something to do with that, or is it totally unrelated?
You mean with the periodicity just of the lattice?
No. Of your when applying your Hamiltonian on your initial state.
Yeah. I see what you mean. You mean this
Yes.
The periodicity
yes, on this
graph.
Yes.
Yeah. Exactly. This is exactly that.
Okay.
It's really the thing is, I mean, for a kind of a standard thermalization process, what kind of graph would we have here? We wouldn't have a graph which goes back to which is kind of closed like this. We would have a tree, an expanding tree, which would like mix all the states. And here, and here, the fact that it comes back to itself, you could take this graph and make copy of it, and you will have the equivalent of the oscillation that you have here.
Okay.
So there is a one-to-one correspondence.
Okay. And so for your starting state, you always choose this left state that you've shown on the slide before, this alternating state. There is this is always your starting point for those.
If you you can begin with so there is you can build a whole family of these kind of states. So the state with a regular pattern, for example, you could, so this is called Z2 states, so referring to their symmetry, and all the state Z4, all that Z3, Z4, so state which would have, for example, black, double white, black, double white, black, double white. This works also for these states. It works a bit less, but it works also. And really, you have to start from these states. If you start from a state which is not in this graph, for example, you will have a completely standard thermalization.
Right. Thank you.
If I can make a comment, I think this periodicity is more general. If you start from a system which is finite, then it has a finite number of eigenstates, right? So if you start from an arbitrary state, you can expand it in these eigenstates. And then when you apply the Hamiltonian, all that does it is add a phase e to the I e times time in front of every one of these states. So in other words, you have a Fourier series now. And if the eigenvalues are commensurate, there will always be a recurrence time because it's a Fourier series, not a Fourier transform.
Okay, okay. I think I see what you mean, but okay. But you're beginning from also you're beginning from a random state.
Yeah, I have to assume that the eigenvalues are commensurate with each other.
Yeah.
I mean, if you have an eigenvalue that is a pi times the other one, then the recurrence time becomes infinite. But what I'm saying is that, I mean, I think I'm helping you in some way. It's not the only model that has recurrence.
Okay, but there is something that is not completely clear for me. So if I can ask a question, if I take a kind of random typical state and I apply the Hamiltonian on it, then I mean, I will obtain another random typical state. So I begin from a thermal state, and I mean most of the what we call thermal state are random states, kind of. So with a spatial structure. So if I begin from a thermal state, and of course I will have a thermal state at the end. But,
no, I'm just doing the same as you. You start from an eigenstate, okay, or a random state, but you know, just one state. But that one state you can expand in eigenstates. Then if you apply the evolution operator to that state, then every one of the components will evolve differently in time because they have different eigenenergies. But what you're expanding your state in Fourier series. So it has to have a recurrence time if the energies are commensurate with each other.
Okay, okay. I see what you mean. I see what you mean. Okay, but you will have a recurrence in the full Hilbert space. Whereas here, the kind of the specific thing with this model.
No. I mean, if it depends how many terms and how many terms you have in the expansion of the original states. I mean,
yeah.
You will always stay within that.
Yeah, in that subspace. Yeah. Okay. Okay.
Now I have another question, which is you didn't define actually this entanglement spectrum. I think or I missed it. Or can you define it again? What is the entanglement spectrum?
Oh yeah, for sure. The entanglement spectrum. This is the name we give at the spectrum of the density matrix, the spectrum of eigenvalues of the density matrix of the subparts. Is this okay?
Okay. Yeah. Thank you.
You can also here I really defined it from the reduced density matrix, but you can also define it by doing an SVD on the full state, singular value decomposition, and you will have the square root of these values, but essentially it's the same thing.
Okay, thank you.
Okay, so if there aren't any more questions, I want to thank you everyone for listening. Thank you again, Martin, for this very accessible talk.
Thanks a lot.
Very straightforward. And I'll see you all next Monday for our next presentation. Bye-bye.
Thanks a lot. Have a nice day.